Welcome to Chapter 6, our final chapter covering practical workflows using PyTorch Geometric and the Materials Project API. We'll learn everything from acquiring data to deploying models in production. This chapter bridges the gap between research implementations and real-world applications. By the end of this chapter, you'll master data acquisition with the Materials Project API, create custom PyG in-memory dataset classes with automatic caching, implement distributed training with data parallel for multi-GPU acceleration, optimize training with mixed precision for speed and memory savings, properly save and load model checkpoints, and deploy trained models as REST APIs using FastAPI. Let's start with the Materials Project API, which provides access to one of the largest computational materials databases. Materials Project is a treasure trove for materials scientists and machine learning researchers. It contains over 150,000 crystal structures computed with density functional theory. Available properties include formation energy for thermodynamic stability, band gap for electronic properties, elastic constants for mechanical behavior, and dielectric constants for electrical response. All data is freely accessible through the API with a free API key. To use the Materials Project API, first create a free account at materialsproject.org and obtain your API key. In Python, import MP restir from mp-api.client and initialize it with your API key. You can then search for materials using various filters like elements, formation energy range, band gap range, and stability criteria. The API returns structured data including material IDs and property values. Crystal structures from Materials Project are handled as PyMatchIn structure objects. These contain the lattice constants, space group information, atomic sites with fractional coordinates, and unit cell volume. You can save structures in CIF format, the standard crystallographic information file format, for visualization or sharing. The getStructureByMaterialId method retrieves the full structure given a material ID. Now let's learn how to create custom PyTorch geometric datasets that efficiently handle Materials Project data. Converting crystal structures to graph format requires several steps. Atoms become nodes with one-hot encoded atomic numbers, giving multidimensional node features covering elements up to uranium. Bonds are created between atoms within a cutoff radius, typically 5 angstroms. Edge features come from Gaussian expansion of interatomic distances. Importantly, PyMatchIn's getNeighbors method automatically handles periodic boundary conditions for crystals. Gaussian distance expansion provides a smooth, learnable representation of distances. The formula computes the exponential of the negative squared difference between the distance and each center, divided by twice the variance. With centers spaced evenly from 0 to the cutoff distance, we get about 40 basis functions. This continuous representation is far more learnable than discrete binning and provides smooth gradients for backpropagation. PyTorch Geometric's in-memory dataset class provides a structured way to create custom datasets. You implement 4 key components. Raw file names and processed file names define the expected file paths, download fetches and saves raw data from the API, and process converts raw data to PyG data objects. The framework automatically manages caching, so processed data is saved to disk and loaded quickly on subsequent runs. The complete dataset pipeline flows from API query to save tensor data. First, query the Materials Project API with your search criteria. Download structures and save as pickle files. Then perform graph conversion to create PyG data objects with node features, edge indices, and labels. Finally, save with torch.save for fast loading. Each stage can be cached independently, allowing you to resume if interrupted. Let's explore how to accelerate training using multiple GPUs and mixed precision computation. PyTorch's data parallel provides simple multi-GPU training. The batch is automatically split across available GPUs. Forward and backward passes execute in parallel on each GPU. Gradients are gathered on GPU 0 for parameter updates, then the updated parameters are broadcast back. One catch, plain-torch.nn.data parallel splits along a batch dimension, and a PyTorch geometric mini-batch does not have one. It concatenates graphs into a single big graph with a batch index vector. So use PyG's own data parallel together with dataless loader instead, and for new code prefer distributed data parallel. Done correctly, this gives close to linear speedup across GPUs. Our CGCNN model architecture follows a standard pattern. The atom embedding layer transforms one-hot vectors to embeddings. Multiple CG-conv layers with batch norm perform message passing with residual connections. Global mean pooling aggregates node features to a graph-level representation. Finally, fully connected layers produce the prediction. The total model has tens of thousands of parameters. Mixed precision training uses PyTorch's torch.qta.amp module to train with a mix of FP16 and FP32 precision. The AutoCast Context Manager automatically uses FP16 for compatible operations. GradScaler handles gradient scaling to prevent underflow in FP16. Benefits are substantial: significantly faster training and meaningful reduction in GPU memory usage. The accuracy impact is negligible. The mixed precision training workflow has specific steps. Wrap the forward pass in AutoCast context. Use scalar.scale to scale the loss before backward. Call scalar.unscale before gradient clipping to work in FP32. Apply gradient clipping with clipGradNorm. Use scalar.step instead of optimizer.step. Finally, call scalar.update to adjust the scale factor. This workflow prevents numerical issues while maintaining speed benefits. Now let's cover best practices for saving and loading model checkpoints. A complete checkpoint should save the current epoch number for resuming training, the model state dict containing all learned parameters, the optimizer state dict including momentum and learning rate states, and current metrics like validation loss and MAE. For best model tracking, compare the monitored metric like validation MAE against the previous best, and save the best model separately. A Model Checkpoint Manager class provides convenient checkpoint handling. It tracks the best score and automatically saves when a new best is achieved. The save method creates timestamped checkpoint files with all necessary state. The load method restores model and optimizer state for resuming training. You can configure which metric to monitor and whether to minimize or maximize it. ONNX export converts your PyTorch model to a portable format for optimized inference. Benefits include significant inference speedup, especially on CPU. ONNX is framework agnostic, so you can run inference in TensorFlow, C++, or other environments. Use torch.unx.export with dynamic axes to handle variable node and edge counts. Be aware that the scatter and gather operations inside message passing have only partial ONNX operator coverage, so always compare the exported model's outputs against the original PyTorch model before trusting it. Let's learn how to deploy train models as production REST APIs. The deployment architecture follows a standard REST API pattern. Web clients send POST requests to the predict endpoint with crystal structure data. The Fast API server loads the trained model on startup. For each request, it converts the structure to PyG data format, runs inference, and returns the prediction as JSON. This allows any application to use your model through simple HTTP requests. Fast API offers several advantages for model deployment. It automatically generates interactive Swagger UI documentation at the docs endpoint. Async processing enables handling multiple concurrent requests efficiently. Pydantic provides automatic type checking and validation of inputs. Performance is excellent, comparable to Node.js and Go. Key endpoints include predict for inference, health for status checks, and docs for interactive documentation. The API schema defines the contract between client and server. Crystal input requires a structure dictionary in PyMetchen format, with an optional CIF string field alongside it. Prediction response returns the prediction value as a float, an optional uncertainty estimate, and the material ID. Pydantic base model classes provide automatic validation, serialization, and documentation generation. The FastAPI implementation uses Python decorators to define endpoints. The startup event loads the model when the server starts, avoiding repeated loading. The predict endpoint receives crystal input, parses the structure, converts to graph format, runs inference with torch.nograd, and returns the prediction. The health endpoint provides status information. Run the server with uvicorns specifying host and port. Let's see how all these components fit together in a complete end-to-end workflow. The complete production workflow connects all the pieces. Start with Materials Project API to acquire crystal structure data. Create a custom in-memory dataset with automatic caching. Train using data parallel for multi-GPU scaling and mixed precision for efficiency. Save checkpoints and track the best model. Convert to ONNX for optimized inference. Deploy with FastAPI as a REST API. Each stage can be run independently and results cached for the next stage. Our optimization strategies provide substantial performance improvements. Data parallel enables multi-GPU scaling for faster training. Mixed precision provides significant training speedup with meaningful memory reduction. ONNX runtime achieves substantial inference speedup, especially on CPU. In-memory dataset automatic caching eliminates repeated data processing. Together, these techniques make GNN models practical for production use. To summarize Chapter 6, the Materials Project API provides access to over 150,000 crystal structures and their properties. Custom in-memory dataset classes enable efficient data loading with automatic caching. Data parallel enables multi-GPU training with near-linear scaling. Mixed precision reduces training memory significantly while maintaining accuracy. ONNX export provides substantial inference speedup. FastAPI enables production deployment with automatic documentation. With the knowledge from this series, you're ready for practical projects. Consider building a custom property prediction model for properties not covered, like elastic modulus. Create an ensemble model combining composition-based and GNN approaches for maximum accuracy. Implement active learning with uncertainty estimation for efficient data collection. Build an interactive web application using Streamlit for material exploration. Congratulations on completing this series. We've covered 6 chapters spanning GNN fundamentals, CGCNN implementation with edge gating, MPNN framework with customizable components, MapBench benchmarking for fair comparison, hybrid approaches including ALIGNN and MegNet, and practical PyG workflows for production. You now have the knowledge to apply graph neural networks to materials science problems. Thank you for learning with us, and best of luck with your materials informatics projects.